Okay, so welcome to this next video in which we are discussing the Western blot. Okay, so we've discussed that the motivation for the Western blot is that we have a mixture of proteins which we are trying to assess whether a certain protein, which we've called protein A, is present within this mixture. Okay, so what you firstly do is you take your solution of proteins and you add it to a loading buffer which contains glycerol and some tracking dye called bromophenol blue. Okay, you then denature the proteins within your protein mixture. Okay, and you do this by heating it up, which destroys most of the tertiary and secondary bonds except a certain type of tertiary bond known as a disulfide bond. Okay, and to break these disulfide bonds, what you do is you use a reducing agent to break those. Okay, now, then what you do is you expose your denatured proteins to sodium dodecyl sulfate, which in solution splits into the dodecyl sulfate anion and the sodium cation, and the dodecyl sulfate anions bind all the way around denatured polypeptides and keep them denatured, basically. Okay, right, and then what you're going to do is you're going to add your solution, which now contains these denatured proteins, into this well here within your polyacrylamide gel. Okay, so let's draw pictures for our three different types of proteins. So remember, originally we said that in our solution we were having three different types of protein: protein A and protein B and protein C. So let's say protein A, the one that we're after, is the biggest. So this is protein A here. Let's say protein B is somewhere in between, so it's a little smaller than protein A. Okay, but it's not going to be as small as protein C. Will that protein C be the smallest? Okay, and here it is surrounded by dodecyl sulfate anions. Okay, so this is protein B. And then finally, protein C, will that be a tiny little protein here with a few dodecyl sulfate anions surrounding it? Okay, right, so this is protein C. So all of those are going into this same well because they're not separated yet. That's what the gel electrophoresis is going to do. It's going to separate them out according to size. Now, we're also going to have two more wells, which are going to be for positive and negative controls. Okay, and I'll explain these more when we've actually seen what gel electrophoresis is going to do. Okay, so we'll say that this one in the middle here, this can be for a positive control. Now, a positive control is something that you want a positive result for, and that will indicate that the experiment is working, basically. Okay, now in the positive control, what we're going to do is put pure protein A, or a known source of protein A. So we're going to go somewhere where we know we have protein A. So we'll take a solution here in which we know we have protein A. So this is some solution here which is a known source of protein A. So there is protein A within this solution. Again, what we'll do to the solution is we'll add loading buffer to it, we'll denature it, we'll add sodium dodecyl sulfate. So again, it will contain protein A that's denatured and surrounded by dodecyl sulfate anions. And this will be put into this positive control well here. Okay, and we'll see that this is going to show us that later on our antibody really does bind to protein A. Then this final third well, I'll discuss these controls more later once we've completed the experimental method and we've seen how it's all going to work. Okay, and in this final well here, what we'll do is we'll put a negative control, and a negative control is something that you want a negative result for, which will indicate that the experiment is valid, basically. Okay, that you're actually showing what you think you're showing. Okay, and for this what you'll use is some any old protein, basically, and the idea here is that we'll show that the antibody in the final step doesn't bind to any old protein. So the general protein that's used is actin. Okay, so generally they use the protein actin. Again, you'll add it to the loading buffer, you'll denature it, surround it by sodium dodecyl sulfate molecules, and it will be in this final well here. Okay, so now we've discussed the positive and negative controls, let's actually discuss electrophoresis then. Polyacrylamide gel electrophoresis. So what's going to happen? So basically, let's draw our polyacrylamide gel again. Okay, so here it is, and we have loaded our solutions containing proteins into these 3 different wells. So here in well 1, we have our original mixture of proteins, which has, remember, protein A, protein B, and protein C within it. Okay, and they're all denatured. The middle well is our positive control. This just has protein A in. Okay, so I'll put that this is A, B, and C. This just has protein A, or it could have other things in as well, but the idea is that it's a known source of protein A. We don't know that yet that protein A is within our mixture. We're assuming that it is, so that I can show you the what will happen, but we don't know is the idea. We're trying to see whether A is in the mixture. Okay, so this is kind of putative up here, whereas this is a known source of protein A, so it's known that protein A is most definitely in there. Okay, and then finally our negative control, which will just contains any old protein, and the usual one that you pick is actin. Okay, right. So what now happens is you stick two electrodes into the gel. So you get 2 metal plates, and you stick these into the gel. So here is a metal plate. I'll colour these in blue. Here is a metal plate here, and here is a metal plate over here. Okay, and originally they're neutral, but we're now going to attach them up to a battery, basically. So we'll get a battery here, and the symbol for a battery is like so, and we'll connect them via wires to the 2 different plates. Now basically batteries are incredible devices. What they do is they ensure that there will be 2 different electrical potentials, basically. So this symbol here is meant to represent the 2 plates within a battery, and this plate here within the battery is going to have a certain electrical potential, and this plate here, which we'll call the bigger plate, is going to have a different electrical potential. Okay, so there therefore will be an electrical potential difference between the 2. So I'll call this electrical potential of this smaller plate here, and then the electrical potential of the bigger plate here. Okay, and they won't be the same. That's what batteries do. They change the electrical potential between the 2 different... Well, they're going to ensure that there is an electrical potential difference between the 2 plates. Now, batteries do not say that this electrical potential is going to be a set value and this electrical potential is going to be a set value. What they do is they ensure that the difference between the electrical potentials of the 2 plates is a set value. So basically, we'll define the voltage from small to big to be the electrical potential difference that you'd experience if you moved from the small plate to the big plate. So let me explain this. If you had a little man in the small plate and he was to measure electrical potential there, he would get some value. If he then moved into the big plate, he would get a different value, this value here. What I am asking is how much would the number on the screen of his machine which measures electrical potential, how much would that change if he moved from the small plate to the big plate? Well, basically, that would be the new electrical potential, which is EB, i.e. the electrical potential in the plate which he's going into, subtract his original electrical potential, the original number on his machine, which was the electrical potential of the small plate. Okay, so this is what is meant by the electrical potential, or the voltage. Voltage is just another word for electrical potential, from the small plate to the big plate. Okay, now basically batteries will set this number. They will be designed so that they are only stable, they're only at equilibrium once they have got a certain electrical potential difference between these 2 plates. And how batteries work is quite fantastic. It's physical chemistry, basically. They use redox reactions, and that's how they create these different electrical potentials on the 2 plates. And basically the whole chemical setup for a battery will only reach an equilibrium once there is a certain electrical potential between these two plates, and therefore a battery will always have a set electrical potential difference between the two plates until the chemical reactions run out, basically. Now, we have attached the big plate to this metal plate over here by a metal wire. So what will happen is that will mean that eventually this plate here has to have the same electrical potential as this plate. So what will happen is some of the charge will move from this plate and it will equilibrate so that all of them are at the same electrical potential. The same thing will happen for this smaller plate. Now initially that will disturb the electrical potential difference between these two plates because we've moved charge away from those plates and onto these plates over here to equilibrate the two. However, of course, the battery, the physical chemistry occurring there, will restore the electrical potential between the two plates. It will only be at equilibrium once the two plates are at this electrical potential difference. So, if the physical chemistry results in these two plates having this a set electrical potential difference, and this plate here, the big plate, is in equilibrium with this plate, and this small plate is in equilibrium with this small plate, then it implies that the same electrical potential difference exists between these two plates. Now, the small plate is going to have a lower electrical potential than the big plate, okay? That's just the way this symbology works. The small plate is always assumed to be the plate with the lower electrical potential, and the big plate is assumed to be the plate with the bigger electrical potential. So we could write this one as the positive plate, and this one as the negative plate, okay? Because this one has a larger electrical potential than this one. And of course, these two plates here are going to become in equilibrium with their plates in the battery. So this one will be the positive plate, and this one will be the negative plate. So, this one, the positive electrode over here, as we can call it, is known as an anode, and the negative electrode over here is called the cathode. Now, basically, you have a more positively charged plate over here. So, we have loads of negatively charged molecules in these wells. Remember, the proteins have all been denatured and are now surrounded by dodecyl sulfate anions, which have negative charge. So they will feel an attraction towards this electrode over here. So what will happen is all of the proteins will start moving through the polyacrylamide gel towards the positive electrode, the anode over here. And also the tracking dye that I told you about, the bromophenol blue, that has a negative charge as well, so that will also move towards the positive electrode. Now, remember, the polyacrylamide gel has this meshwork of polyacrylamide molecules, okay? And this is going to provide a certain amount of resistance to the movement of these polymers of amino acids, which are called polypeptides, which we know we have in these wells that are trying to move through the polyacrylamide gel, okay? Now, proteins which are smaller will encounter less resistance to their movement and therefore will move through the polyacrylamide gel faster, basically. So they will move a greater distance in a certain amount of time, whereas proteins which are larger, okay, those will encounter more resistance and they will take longer to move. Now the quickest thing to make its way through will be the tracking dye, the bromophenol blue, because that's not a polymer at all, that's a small molecule. So that will move through. So I'll firstly show what that will do. Basically, the bromophenol blue will move forward and it will get to some point, okay? And when it gets nearby the edge, basically, you will want to stop the process. So you will remove the battery and therefore stop movement. So that's the purpose of the tracking dye. It shows you it shows you when to stop the gel electrophoresis. And by the way, this process of the proteins moving because of the electrical gradient is known as electrophoresis. Okay, so basically, you will wait until the tracking die gets near to the edge, and then you'll want to stop the electrophoresis, because you don't want the proteins getting to the edge, and we know that all the proteins will be to the left of the bromophenol blue. So as long as we stop the electrophoresis process before the bromophenol blue gets to the edge, we know that certainly the proteins haven't got to the edge. Okay, so now let's discuss what will happen to the proteins in this well 1. So remember, we were assuming there were 3 proteins, protein A, protein B, and protein C. Now C was tiny, so in a certain amount of time, which is how long we've been running the electrophoresis before we stop it, because the bromophenol blue has got almost to the edge, the C will have got furthest of these 3 proteins. That won't have moved as fast as the bromophenol blue, but maybe it's got to here. Okay, so here is where protein C has got to. Okay, protein B won't have got as far because it's slightly longer, so it might be here. And protein A was massive, so it might still be back here. But all of them will move through the gel, and how much they move is determined by how long they are. So the longest polypeptides will move the least in that amount of time, and the shortest polypeptides will move the most in that set amount of time. Now, our positive control just contained protein A, so of course that will have got to the same place as the protein A in our mixture up here. And finally, actin might be any old place, I don't know, it could be, let's say it's over here. Okay, so here is actin. Right, okay, so now we have done the electrophoresis. What we're now going to do is we want to be able to visualize the results of this electrophoresis. This is all lovely, but we can't see any of this. These are proteins, we can't see them. We can't see these lines. I've put them there to show you conceptually what's happened, but we can't actually see them, so we want to visualize it now. So what we're actually going to do is take a snapshot of this, basically, onto a different membrane which we can probe with antibodies, because we can't just tip antibodies onto the gel. It'll make a mess, basically. So we first transfer it onto something a little bit more substantial. Okay, so the next process that you do in gel electrophoresis is something that's known as electrophoretic transfer. Okay, so electrophoretic transfer, and basically what we're going to do is transfer these, we're going to transfer each of the, well, a little bit of each of these proteins onto another membrane, onto a nitrocellulose membrane. So, basically what we'll do is we'll take the gel out. Okay, so we've ended the electrophoresis process. Now there's no electrical potential difference between the two sides, so the proteins have no reason to move anymore, so they won't be moving. Okay, and what we'll do is we'll take our gel out, so here it is, let's say, and what we're going to do is we're going to put another membrane underneath it. Okay, so I'll show this here. And this is, by the way, known as a sandwich preparation because of the different layers. Okay, so here is another membrane underneath it. And generally the membrane you use is something known as a nitrocellulose membrane. There are other things that you can use, but nitrocellulose is generally the most commonly used. To generalize it, because of course it's not necessarily nitrocellulose, instead we could call this a blotting membrane. So alternatively, to be more general, we could call this a blotting membrane rather than specifying that it's a nitrocellulose membrane. But often you do use nitrocellulose. Right, so let me colour these in different colours. So we'll have the gel in green here, okay, and then underneath we've got the nitrocellulose membrane in pink. So we've stacked them one on top of one another, and of course I've shown it with a great gap between them so that I can actually show it to you and it will be obvious what I mean, but in reality, you know, this will be pressed up against the gel on top here. Okay, and this thing that you've created here is known as a sandwich, basically, okay, or a sandwich preparation. So you produce a sandwich preparation, and there are a few more layers that you put in, but those are frankly just technical, okay, to protect the equipment. So these are the essential 2 layers as far as conceptual understanding is concerned. And then what you're going to do is you're going to apply an electrical potential difference across these two. So then what you'll do is put underneath another anode, basically, another metal plate. Okay, so here's a metal plate which is going to be positively charged, and then above it what you'll have is a cathode. So here is another metal plate which will be negatively charged, or at least there will be an electrical potential difference between the two. So again, these will be connected to a battery, and this one will have the small plate of the battery, and this one will have the large plate of the battery, so that just as between the two plates of the battery there is a set electrical potential difference, between these two plates now there is a set electrical potential difference. Now, remember, all the proteins in the gel are still negatively charged, so they're going to want to move towards the anode here, away from the cathode at the top. Okay, so this is the anode, and this is the cathode. So what's going to happen is the protein in the gel is going to move down onto the nitrocellulose membrane, and if we've stacked everything on perfectly, the protein will move in exactly the same position as it was on the gel onto the nitrocellulose membrane. So hopefully we will get an exact snapshot of this information here on the nitrocellulose membrane. So let's now look at our nitrocellulose membrane. So it should be a snapshot of what we had on the gel, basically. So we should have protein A here, protein B here, protein C here, and this was our mixture. Then in our positive control we have protein A here, and in our negative control we have actin over here. So this is now our nitrocellulose membrane. Now, what is so special about nitrocellulose? Well, basically, nitrocellulose binds to proteins absolutely fantastically. Okay, so as soon as the protein arrives on the nitrocellulose membrane, it instantly binds to the nitrocellulose membrane. Now, what are we going to now do? Well, basically, we're going to use anti-protein A antibodies, i.e. antibodies which bind to protein A, to detect the protein A on this nitrocellulose membrane. Now, there is a problem with that antibodies themselves are protein molecules, so they will bind to the nitrocellulose membrane anyway. So if we chuck anti-protein A antibodies at the moment, it will just bind all over this nitrocellulose membrane, and it will do that whether there is protein A in this first mixture or not, basically. So that will be useless. So firstly, what we have to do is a process known as blotting, which is basically where we saturate all of the places that protein could bind to the nitrocellulose membrane. So we want to bind so much protein onto the nitrocellulose membrane that no more can bind, basically. So the only way the anti-protein A antibodies can bind now to the nitrocellulose membrane is by binding to the protein A, which is bound to the nitrocellulose membrane, rather than just binding directly to the nitrocellulose membrane. Okay, so generally what you do is you douse the nitrocellulose membrane with a protein known as bovine serum albumin. Okay, so it's albumin from cows. So bovine is B, and then S, serum, and then A, albumin. So BSA is short for bovine serum albumin. Okay, and dousing the nitrocellulose membrane in bovine serum albumin uses up all of the protein binding sites on the nitrocellulose membrane, and then means that if a protein if an antibody now wants to bind here, it's going to have to bind to one of the proteins that is already bound there. Okay, now, excuse me, what we will now do is we will use an antibody that is against protein A. Okay, so here is an anti-protein A antibody. And what will happen now is if we expose this nitrocellulose membrane to the anti-protein A antibody, the anti-protein A antibody should bind to the protein A in this line here, and also the protein A in the positive control. Okay, it should not bind to protein B, protein C, or the actin. Okay, right. And we will continue this discussion in the next video.